this computer, share my screen. Okay, so today I want to talk about a different technique that is useful for certain type of problems. And I would say that this is definitely something that's a bit advanced, but um, I would say if you have taken 3620, this should not be difficult to understand, although you might not have seen this before. If you have not taken 3620, it still should not be so bad, but maybe you need a little bit more thinking because it's less familiar. So last week we talked about something called suffix, sorry, not, we talked about something called Fenwick trees. And just a reminder, what is Fenwick tree is something that allows you to manipulate the cumulative sum or the partial sums of an array while allowing you to update the elements in the array. And you can query what is the partial sum at any particular point. You can update values and have all the partial sums updated, etc. Everything in basically log n time. Okay. So today I want to talk about something that's a different kind of data structure. And this data structure, it's called segment tree. So again, it's a tree of some kind. Okay, this thing is here. So it's a tree of some kind, and it's a tree that stores segments. What is a segment? So again, there are many different variations, but again, let's imagine that you have an array. So you have an integer array, a from 0 to n minus 1. Okay, and you want to be able to do a few things. You want to be able to update the values of AI to some other value. And then you also want to be able to query something, this is a little bit vague here, something about a range, A from L to R. Okay, so you're given the left and right endpoints of an array, of a range in an array, and you want to ask something. Now, what are these something? What are some examples of these something? What can you ask? So examples, it could be, what is the maximum of the range? What is the largest number in the range? It could be, what is the minimum? Could be, how many, I don't know, zeros are there? Or whatever it is. It doesn't have to be zero, it can be anything. It can be any particular value. Could be, what is the sum of this range? And there can be many, many more things that you can ask. Now, of course, if you're looking for the sum, then that's not something that's new because you could have done it with a Fenwick tree, right? Last time we talked about Fenwick trees. So Fenwick trees allows you to update elements by incrementing or decrementing. So if you want to update a particular value, you just have to figure out what is the increment you have to use to get to that new value. And you also can get partial sums of A0 all the way to any particular location. Let's call it a K. So you can compute partial sums from 0 to K. And if you want to do if you want to know the sum from L to R, then that's the same as the partial sum from 0 to R minus the partial sum from 0 to L minus 1. So if all you want is the sum, then Fenwick tree would do the job. Okay, but if you want to do other things, then Fenwick tree doesn't really work. Okay, so what is a segment tree? So in a segment tree, you have nodes, and the root would represent the range from 0 to n minus, let me draw the node bigger because I'm going to put a lot of things in it. from 0 to n minus 1, and it also stores whatever query you are interested in. So if you're interested, let's say you're interested in the maximum of a range. If this is the query that you want to answer, then not only will the root node will represent the entire array, and it will also store the maximum of A0 all the way to n minus 1. Okay, so somehow you have the entire array, the maximum. It also has two children. What are the two children? The left child would have basically the range n over 2 minus 1. So basically it's the left half. So the left half of the array and the right half of the array are the two children. And minus 1. And then, of course, each node would also store the maximum of the range that it represents. Okay. And then it goes on, keeps on going. This would then subdivide again. It'll go, the next one will be 0 dot dot n over 4 minus 1. And this would be n over 4 dot dot n over 2 minus 1, etc. And then eventually you'll get down to the root, the leaf nodes, which are nodes that are just have the single, the range is just a single element in the array. So let's have a concrete example. So let's say you have an array A, and how many elements do we want to have? Let's make it 7, okay? Normally, when you divide things by 2 all the time recursively, you want things to be a power of 2, but I just want to show you that it works even if you don't have powers of 2. So these are the indices. And then, I don't know, we'll just make up some number. Okay, so these are the array contents. So your segment tree, when you build it, the first node will be from 0 to 6, and it will know the maximum of the whole range, which is 6. Then you split it into left half and right half, and because it's odd numbers, you have to decide whether the left one is bigger or the right one is bigger. It doesn't really matter, you just have to choose one. And then you also have to store the maximum of that range. So 5 is the maximum from 0 to 3, 6 is the maximum of 4 to 6, and then 0 to 3, you can break it to 0, 1, and 2 dot dot 3. The maximum here is 5, the maximum is 4, and then finally, when you get down to the leaf, it's just 0, and then the maximum is 4, the maximum is 2. Okay, the leaf node is pretty straightforward. And then here, this is 4 dot dot 5, the maximum is 6. And then 4, the maximum is 0. 5, the maximum is 6. And 6, the maximum is 3, like this. Okay, does it make sense how this tree is built? Okay, the idea is that when you build this tree, you would actually build it bottom up, right? So you can easily build all the leaf nodes because that's just the array element. And then you can combine the 0 and 1 into 0 dot dot 1 into a subtree, and the root of the subtree would just be the maximum of the two children. And then here, for example, this 5 is the maximum of the two children because that represents the maximum whole range, etc. Okay, does that make sense?
Yep.
All right. So now that if you build such a tree structure, how long does it take to build? Well, basically the number of nodes, you might think that the number of nodes is a lot, but actually the number of nodes here, if you look at the size, the total number of nodes is actually linear. I started with 7 nodes, but how many nodes do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I have the total of 13 nodes. And if you're using a binary tree, so basically you have a binary tree and the number of leaves is exactly n, right? The number of leaves is exactly the number of nodes you have in your original, number of entries you have in your original array. And it turns out that if you have n leaves, the total number of nodes in a binary tree is at most 2n. It cannot be more. Okay, so it turns out that, and in fact, you can actually say it's, I believe it's 2n minus 1. It's always true. So basically, the space, it's linear. So it's not that bad. That's the first important thing. How long does it take to build this thing? Well, it's also not that bad because there are only 2n nodes, basically. So the amount of work that you have to do is also linear. Okay. How do you write this code? Well, you do something like build, and then you have a left endpoint, you have a right endpoint, something like this. And then originally you pass in 0 to 6 like this. And then recursively, you would say, well, if left and right are the same, then you just build a leaf node and that's it. And return a pointer, let's say, to the parent. So maybe this is like a node pointer if you're building a tree with node pointers. And then if the left and right endpoints are not the same, then you sort of figure out how you divide left to middle and then middle to right or something like middle plus 1 to right. And so you can take left plus right, divide by 2 to get the middle, for example. And then you would recursively call the left half, you'd recursively call the right half. They both return a subtree, and then you can build a new node that link up the 2 subtrees and compute this number as appropriate, right? So if this is a max, then of course, if this number is a max, then you take the max of the corresponding numbers in the 2 subtrees. If you're trying to do min, then you do min. If you're trying to do the sum, then you add up the numbers instead. And there are other things that you can do. So that's basically how you build a tree. As with most tree algorithms, you do things, it's easiest if you do things recursively. Now, even though I draw it like this, like a tree, and I tell you that you can allocate nodes and you have the left pointer to your left child and right pointer to your right child, it is actually not the best way to do this. The best way to do this, because this tree is regular, the best way is actually number these nodes like this. You might have seen this if you might have seen this heap or priority queue implementation. I don't know. Some of you may have seen this in 3620 or even 2620, but if not, that's fine. If you number these nodes this way, the way that this tree is built, if you make sure that when you have an odd number, you always make the left side a little bit, the one that's a little bit bigger than the right side, then you can guarantee that you won't have an empty level until the end. And if they're empty level, it's always on the right side. Okay, so there are no holes in anywhere. And if you do that, then given any particular index, if you know what the index is, if they pick any index, then the left child, it's always 2k plus 1. And the right child, it's always 2k plus 2. So pick any number, 4, for example. 2k plus 1, that's 9. That's the left child. 2k plus 2 is 10. That's the right child. Okay. And then if you want to know who your parent is, if you care about that, then the parent, it's always k minus 1 divided by 2 rounded down. Okay, so if you take any node, let's say 4, 4 minus 1 is 3, 3 divided by 2, and then rounded down is 1, and you get your parent that way. So you can, so what I'm saying is, in fact, you don't need to actually use an array. You don't need to use pointers and so on to make a tree. You can just use an array from 0, 1, 2, up to 12. And then all you have to do is store the maximum of that node. Those are the only things that you have to store. 4, 2, again, running out of space, 1, 0, and 6. And just using the indices, you would be able to figure out how to get to the left child, how to get to the right child. And so this is sort of an array representation of the binary tree. And it only works because there are no holes until the bottom right. So if there are any holes in the complete binary tree, it's only in the bottom right. Okay, anyway, so that's how you would represent it in memory. So now the question is, does this actually work when I tell you that I want to support 2 operations, right? So what are the operations I want to support again? I want to be able to update any particular elements to a particular value. And then I also want to be able to ask what is the maximum or whatever operation you're using, maximum of a range, whatever endpoint that might be. Okay, so let's look at how you do that one at a time. So let's say update. So let's imagine I want to update a bracket, what's a bracket 0? I want it to become 8. Okay, so I want this to become 8. So of course, many things will be changed, right? Many of the maximums will change, but notice that this subtree here, this subtree doesn't include zeros, right? 4.6, 4.5, it has nothing to do with 0. So none of this has to change. The only thing that have to change are the nodes whose range includes 0. So what do you do, right? So what do you do? How do you do this update? Well, you look at, basically you look at the index that you want to update, and you start from the top again. So again, you have a recursive function that starts with the top. And if this range does not include k, you're done. Okay? So if this range does not include an index that you're changing, you don't have to do anything. But if it does, and it's not a leaf, then what do you have to do? You have to recursively call update on the left and recursively call update on the right. Okay, so I recursively call update on the left and recursively call update on the right. And when they're done, then I have to update my maximum. Okay, so this is kind of, if you're thinking about tree traversal, this is sometimes called post order traversal, because you have to do something with the subtrees, and then when they're done, then you can compute, you can update your own value. So here, 0 is included in this range, so I have to recursively call the left subtree, recursively call the right subtree. Now, when I call it recursively on the right subtree, it's going to say 0 is not included in this range, so there's nothing to do, so it's going to quit right away. So nothing will be done over here. But on the left-hand side, it's going to do something. It's going to, again, ask, is 0 included in my range? Yes. Okay, is this range a leaf? No, so I got to recursively call the left, got to recursively call the right. Again, when I call recursively on the right, nothing happens, so it just stops. I recursively call the left. So again, it says, is 0 in this range? Yes. So I got to recursively call the left and the right. Again, the right doesn't do anything. Recursively call left. Now here I have a leaf. So I don't recurse again. I just update this number to 8. Then I back up here. When I back up here, what am I going to do? I have already recursively called my left and right subtree. So I'm going to recompute this number as the max of the 2. Then I'm done. I back up here. I already recursively asked the left and the right to update. So again, I update myself to the max of the 2. And similarly, when I get up here, I updated myself to the max of 2, and I'm done. Okay? So notice that actually you can convince yourself that whatever index you're using, you will basically just start from the root and follow down some path. Follow down some path from root to the leaf, basically. It might not always be this path, right? If you try to update a bracket 3, you start from here, then here, then here, then here. In any case, the important thing is whichever index you're trying to update, you're always going to be following a path from the root to a leaf. So the complexity or the number of steps you need to use is basically limited by the height of that tree. And the height of the tree is always logarithmic, log 2 of n, right? So here, there are only 4 levels, right? And you have about 8, basically 7 or 8 nodes. So log of 2 of 8 is 3, but then you have to add 1 for the root. So basically it's something like the number of levels, it's basically log of n to the base 2 plus 1 or something like that. But the plus 1 doesn't really matter. So the point is you can update the value and update all the things that you're storing at the node that matters. This can be done in log of n time. Okay? Does that make sense? How you update this?
Yeah, I think so.
Okay, so now how do we ask the maximum or whatever it is that you're storing in each node? Could be maximum, could be sum, could be other things. How do you compute the maximum of a certain range? Well, if somebody asks you, what is the maximum of A0.6, so the whole array, and you say there, it's easy. I read this thing, it's exactly that, I'm done. I don't have to do anything, right? It's just right here. I just read it, that's the end. Okay, but that's not very interesting because most of the time you're not just going to ask something right at the top. So you might say, okay, well, what about asking for something like the range 0 to 3? Well, you could come down here and you say, okay, 0.3. It's not 0. The node is 0.6. That doesn't work, so I can't get the answer from here. But I know that the left side is 0.3, the right side is 4.6. So I'm going to go down the left, and then I realize, this is exactly that node. I'm done. I just return the 8. Okay, but that's also not that interesting because what I'm looking for is it found in some node. So what if I'm interested in getting 0 to 2.5? Okay, so I want to know the maximum from 2.5, which is not anywhere, right? I have no node that says 2.5. So what do I do? Okay, so this is where things gets a little bit more interesting. So let me write this trace here. So I'm trying to find the maximum of A 2.5. And what I'm going to do is I'm going to start at the root, which is the root represent the entire array. So the first thing that this algorithm does, and this is again a recursive algorithm, if you ask me to find a range 2.5, and I'm at a node of a certain range, if there's no overlap of these two ranges, then I can just say, basically I can return nothing, right? So if, for example, that the roots is 0.6, the node that you're looking at 0.6, and you're asking me what is the max of A, let's say the array is bigger and you're asking me this range, then I can just say there's nothing to return. Okay, there's no maximum. Okay, that's kind of the simple case. The other simple case, of course, is that I'm asking you what is the max of, let's say, 2.5, and the node that I'm looking at is exactly this range. If it's exactly this range, then of course, all I have to do is read off the maximum, store the node. So that's also an easy case. The what's not so easy is when the range overlaps with your query range, of the query range overlaps with the range of a node, and it's not exactly. So then what do you do? Well, then you have to go through the split. So you know that the root, it's going to split into 0.3 and 4.6. Okay. So what do you do? You're going to recurse on the maximum of A2.5 on this range. Okay, so you're going to recursively call your function twice, one on the left side, one on the right side. So on the left side, again, you ask, what is the maximum 2.5? And on the right side, you ask that again. Now, the next stage, each of those recursively would say, wait a minute, you wanted to ask for 2.5, but I am, in my node, I'm only 0.3. So that doesn't actually make any sense. So I'm going to, when you ask me 2.5, but I only have 0.3, I'm going to pretend that you asked me 2.3 because it doesn't relate. I don't have 4 and 5. And over here, I do the same thing. I'm going to pretend that you asked me 4.5 because I don't know anything about 2 and 3. Okay? And then whatever these two things returns, I'm going to take the maximum. Okay, so now again, this says, okay, 0.3 includes 2.3, great, but it's not exactly the same. So what am I going to do? This is going to split again into 0.1 and 2.3. And then I'm again asking for the maximum from 2.3. So here I can return the answer. This is exactly this node. And I know that I can return the answer 5. Here I just say, well, my node has the range 0.1. You asking me something that's not even in my range. So I can just return, I guess one trick is to return negative infinity. So something really small, because when you take, when you return these numbers and this node would then combine these two values by taking the max, returning negative infinity basically means that you take the other one. So this will send the 5 back up. Over here, 4.6, well, 4.6 is not the same thing as 4.5. So what is it going to do? It's going to split again. Just follow this tree, right? It's going to split into, I'm just going to draw it like this, 4.5 and 6.6, I guess. And then again, you're asking what is A4.5, so you found it right here. And this one, it'll just return negative infinity because it's not even in the range. And then this will return 6, and then you will then take the, go back to the roots of the computation, and then it will return the maximum of these two numbers that return 6. Okay, so that now I'm drawing two trees here, but this thing here is the data structure, is a segment tree. And this thing is not actually stored anywhere. This is the recursion tree. This is actually the recursive calls of my algorithm to figure out what is the maximum of certain range. Okay, does that make sense?
Yep.
Now, then there's a question of, is it a good algorithm? Like, is it fast enough? Right before, when we're talking about updating, we said we always go from root and follow some path to a leaf. So the number of paths, the number of times I have to do this is basically the height of the tree, which is logarithmic. But here is maybe it's not so clear, because what am I doing? I'm starting from the root, but then I'm splitting to the left, I'm splitting to the right, and then each time I might be splitting on the left and right, and each time I can be splitting both sides. And then if I really split both sides everywhere, then I will be touching every single node, and there will be linear time, which is no better than just doing the simple thing that loops do from L to R to compute the minimum. So the question is, how bad is it? So let me make things in general. Right, so this is if you have n nodes, so I'll just kind of draw things a little bit bigger like this, and so on. Okay, there can be many levels. So if you're going to ask for a certain range, whatever thing you're trying to compute in this range, there are three possibilities. It could be that this range is completely inside the left half. Right? So if it's completely in the left half, you'll recurse this way and keep going. You may decide to recurse this way, but then it will cut off right here. So you will only go down, essentially you only go down one path. So you don't have to worry about exploding on you. If every time you recurse, you only go down one path, you're good in terms of getting logarithmic time. So this is case one. Case two is the same idea, completely in right half. In that case, you only go down the right half, the right subtree. Third case, what is the third case? You are exactly the same as the node. So whatever range you're querying is exactly what the node covers. In that case, you don't recurse at all. Okay, those are the three good cases. And then the rest, that's the potentially bad part. Okay, so what's the potentially the bad part? So if you imagine, and then maybe this time I will use some specific numbers because it might be too messy to work out general case. So let's say that you have 0.99. You have exactly 100 numbers in the range. So this is 0 to 49, 50 to 99, and then you have 0 to 25, 24, 25 to 49, 50 to 74, 75 to 99, let's say. And let's say that you're trying to query some
Hey, Howard, I think you muted yourself.
Oh, sorry. I don't know exactly. I must have tried to move this thing out of the way and then accidentally. Okay, so if you're trying to find A30 .80 is set the maximum in this range, then what you're going to do is you're going to have to split into left side and right side. To the left side, you will go 30.49, 50.80 on the right. And then here, you would have to split again. You'd have to split 25.49 and then 30.24. Right. Oh, I guess in this case, you actually just go this way. Okay, hang on. Let me make it something smaller so I can show something better. Show it this a little bit better. So 25.49, and then you're gonna on this side you're gonna search for 10.24, and then down here you might go from 0.12 and then 13.24. So you go 13.24, 10.12, etc. And then here 50.80, you go 50.74, 75.80, and this will stop. And then over here you would have to split again. So if you split again, this will be, I don't know what it is, 75 to, let's say 82 or something like that, and then 83 to, okay, I probably got it not right, but probably closer to 85, and then 86 to 99, whatever, some way to split it. And then here you only go this way, 80.80, you don't go this way, and then you keep going, and then this goes, I don't know, 75 what is it? Let's say 80, and then you go this way, and then you don't go the other way because the other way is too big. Okay, now, what am I trying to show? What am I trying to show is, it's true that you split both ways. And then you say, oh, if you split both ways all the time, you're not going to have the logarithmic time. But notice that when you split both ways, the right end point of this range that you're asking is always as big as possible on that side, which is 49. So what would I mean? What does that actually mean? So when I go to the right, you see I stop. If I go to the right, I stop. Here, I go to the left and I split again. If I go to the right, I stop. So once I go to the left once, every time I go to the right, if I have to go to the right, it will never split again. It will never kind of, so if you have to go both to the left and the right, then the right side can never split again. And similarly, when you go one step to the right, if the next node you go both to left and right, the left side can never split again. So here, this time, you go left, but the left side did split again because you didn't go both sides. But if you had to go this way, then the left side cannot split again. So why? So for example, look at this. If I have to go both ways, that means 24 must be part of the range. In that case, 25 must be part of the range. I already know that 49 is part of the range because I wouldn't have split both ways if 49 was not part of the range. So that means that this is exactly that whole range, and it must not split again. So I know it's a little bit confusing, but basically the idea is once you go both ways on the first step, then at that point after that, whenever you have to go both ways, then one of them must not split again. And so basically the only time you go down, keep going down, you will only be able to go down on one path. So basically on each side, you would do about big O of log n work on each side. And then you multiply that by 2, but it doesn't really matter with log n. Now, the code for this is actually a lot easier, perhaps, maybe actually is a lot easier to describe, to write than all this picture that I drew. because you use the power of recursion, and also the fact that, how do I put it? The fact that all these nodes are actually array indices. So what does the code look like? For example, let's say I want to know what is so I have my underlying array A bracket, whatever, 0 dot dot n minus 1. And then I also have what I would call a segment tree array, which has 2n entries. Okay, and you have to build it with some code, but so how do I build it? So the easiest way to build it, I guess, so you pass in your array A, you pass in the range left and right, like this, and then also the index of the node in the tree. And originally, so you start everything with the call build A 0. Now, okay, now you have to be careful. Do you use L dot? Do you use the standard C++ convention that R, the right endpoint, is one past the range or not? So let's actually do that. So the R, I guess, when I was doing my slide, the explanation, I said, if you use L and R, then I'm asking for the range, this range. But the way that I write it now, actually, if you give me an L and R, I'm going to give you the answer for this range. So I'm kind of lying a little bit before, just because in C++, the range usually is specified with the right endpoint, one past the array, one past the range. So what does the build look like? Okay, so if if R minus L is equals to 1, then I'm basically at a leaf node, meaning that my range is exactly one element in my array. Then I just say the segment tree at that node is exactly A bracket L. Return. Okay, otherwise, I've recursively called build A, and then, oh, wait, somewhere I have to compute the middle. So mid, I guess I use, let's just say M is equals to L plus R minus L over 2. So this is the middle. And then I would just say build the left half. And I set that 2 times node plus 1 is the left child. Then the right side, 2 times node plus 2. And then I just say st node is the max of st 2 times node plus 1. Okay, forgot the star, but you know what I mean. 2 star, 2 times node plus 2. So I basically then say this is the maximum I store in my node, which is the maximum of the entire range. It's just the maximum of the left subtree and the right subtree. And that's all there is to build the tree. And then what do I want to do? Update. Update. So again, so you want to update A bracket K to value. And then I always have to pass in the left, right, and the node. And you always, you always initialize, oh shit. Okay, am I back? You always,
you didn't leave, but we can still hear you.
Okay, do you still see my sharing screen?
Yes.
Okay, so initially these are always 0, n minus 1, so n, because I said that one past the n, and 0. So how do you update the value? So again, if L R minus L is equals to 1, so you leave, then that's easy. You just say st node equals to the value. Actually, why do I even need the k? I don't even need the k. Do I? Oh, wait. Yeah, of course I need the k. Wait, sorry. Hang on. I did something stupid here. Okay. So if L less than or equal to k and k is less than r, not. Okay. So what's going on here? So basically, if I'm trying to update a bracket k equals a val, and the node specify a range that doesn't even include k, then I just do anything. So now I know that the node has k in the range. So then I say if r minus l is equals to 1, meaning I have a leaf node, then I just say st node equals to val return. Okay, and then I do the standard thing. So maybe this time I'll just declare left. So just left equals to 2 times node plus 1, and right it's equals to 2 times node plus 2, or you can write left plus 1. That's the same thing. And then you can say m is equals to L plus R minus L over 2. Then you would just say update K, val, L, and M, and then left. So again, recurse exactly the same way. Update recursively with the val, M, and R on the right subtree. And then when you're done, st of node is equals to max of st left and st right. Okay, so that's update. So again, it looks like a lot of code, but actually it's not really that difficult, because you just have to remember, look at the base cases. Base cases, the node doesn't matter, or the node is a leaf. And if there's neither of those base cases, then you recurse on the left, recurse on the right. And then finally, if I want to create a max of a range, let's call it max range. So again, you would tell me L and R and the node.
Mom, are you coming?
Oh, sorry. Now this time it's a little bit tricky, because I have 2 left and right. I have a left and right that corresponds to the node, and I have left and right that corresponds to query. So I'm going to make the distinction here and say query left, query right, that's what you're querying. Then there's the left and right of the node, and then there's the node ID. And initially, again, you would call this with 0 and 0, but of course the query left and right would depend on your query. Okay, so what do, right? So first of all, if the range that you have, it's exactly the same as the range that's given in the query, then you're done. You just return. Okay, that's the easy case. And then what other things? If the range, the query range is less than the left range of the node, or if the query right left it's greater than the right range of that, that means that the query range doesn't actually overlap with the node range, so you basically return some sort of a negative infinity, or you return some invalid value that doesn't affect your result. Okay, Now you're going to compute M left and right exactly the same. I'm not going to write them again, but exactly the same formulas as before. Equals to dot, dot, dot. I'll just leave it at that. And now what you're going to do is you're going to also then say return the max of the recursive calls, max range, query left, query right, left M, and then the left node index. And then you do the same thing with the right side. And that's almost the end. Now, why do I say almost the end? Because I haven't actually adjusted anything. So what do you mean by that? If I'm querying, let's say, the range, let's say 0 dot dot n is 0 dot dot 99. So 0 dot dot n minus 1, 0 dot dot 99. So you have 100 elements. That's my original array. And let's say my query range, so this is L and R, and my query range, and again, my query range, because of the way that I write this, the query range is also from QL dot dot QR minus 1. The QR is also 1 past the n. Okay, so if let's say I'm trying to query, what did I say, 10 to 80. Something like that. Okay, so 10 to 80, or 10 to 79. So my query range is 10 dot dot 79, and my original range, L and R, is 0 dot dot 99. So then I say, okay, the only way I can do this is I split. So I split it into the middle. So the middle is 50, let's say. So then it'll be 0 dot dot 49 and then 50 dot dot 99. But now when I call things recursively, I'm going to have a little bit of an issue because my 0 dot dot 79 is still my query. And when I query 0 dot dot 49, the query is 0 dot dot 79. And then the next level, L and R minus 1 will be 0 dot dot 49. This 79 will never match anything in the node because it's 79, it's too big. And I have to actually adjust this 79 to something that's more in range. So what do I have to do? So basically up here, before I do anything, I have to say, if the query range, the right endpoint, that's actually the right endpoint is bigger than the right endpoints, then just make it the same. Okay, and similarly, if the left endpoint is too small, then make it this. Okay, and that will make sure that things work correctly. And that will work even if you have the query range being, I don't know, the query range could be, I don't know, 0 to 49, and then maybe your node range is, I don't know, 75 to 100, let's say to 99. In that case, this will apply, and you set the left of the query range to become 75. So the query range would become 75, and you might say, that doesn't make any sense, but that's okay. That's okay because you will still fail on this check here. The query range of R is less than L, so we'll just quit right away. And then you can also say that when you have if you have a range where the left endpoint is bigger than the right endpoint, it means that it's an empty range. So you can kind of cheat like that as well. So anyway, the main thing is you have to adjust the query range so that it's the range that's applicable to that node. But otherwise, that's really the code, okay? And that's basically it. So the explanation probably it's a lot longer than actually writing the code. And you know, whether you're looking for if you're not looking for the maximum, but maybe you're looking for the sum, well then you would just change it to be sum and then sum, and instead of max, you just add the two together, right? And you can do this similarly for many different functions, whether it's sum or max or other things. Okay, so this is the segment tree. Does that kind of make sense?
Yep.
Now, I want to also show you something that maybe you wonder why I will show you this, because this is kind of like a inferior version of what I told you. Okay, so but maybe it's still good to think about what's going on. So if you're going to do this basically this is what is called range maximum query. You want to be able to ask the maximum of any particular range and be able to update your array. And this max, of course, as I said, you can change it to a different function. Doesn't have to be max. Okay, so if you do segment tree, then update takes log n time, and query takes log n time. So it's a nice balance, right? It's always log n time. What if you use standard array representation, right? So you don't do anything special. You just put all the numbers in an array, then update is very fast. Right? You just change the value of the array. But when you actually, I want to know the maximum in a range, you have no choice but to actually loop through the whole thing. Okay, so that's not great. What other things can you do? Right, so we have segment tree, which basically split the array into two halves at each step, and you get the standard logarithm time. You have this other way, which is very fast in one way, but potentially very slow in a different operation. So here's another idea. Let's split them into blocks of some other size. Okay, we'll just call it size B, where we won't talk about how big B is. So what does that mean? You have an array of size n, and I'm going to divide them into blocks of size B. So the first chunk would be 0 to b minus 1, then the next chunk would be b to 2b minus 1, and so on. Okay, and if you, maybe just to make things more concrete, maybe we'll say, I don't know, you have an array size 50, and we'll use size of 10. Okay, just to make it more concrete. Then you will end up with 5 blocks, okay? So 5 blocks. This is 0 to 9, 10 to 19, 20 to 29, 30 to 39, 40 to 49. Okay, so what am I doing here? I'm going to store, in each block, I'm going to compute the maximum, just one single number, the maximum of A from 0 to 9, maximum of A from 10 to 19, etc. So I can pre-compute 5 numbers. When you give me the array, I can compute these 5 numbers, right? First, the maximum first 10, maximum second 10, and so on. Now, if you want to update A bracket, I don't know, 27 equals to 5, what are you going to do? You're going to go in and update that number, but you're also going to have to update the maximum of A dot dot 29. And updating this, if you just, because the size of the block is 10, you need to do a loop of 10 steps. Or in general, updating takes this much time, because basically how much time you have to spend updating the maximum of the block, it's the size of the block. Okay. Now, what about currying? Okay, what about currying? If you want to know what is the maximum of A, I don't know, 25.28, what are you going to do? Well, it's not any of these pre-computed maximum, so you just go into this, array, look at those 4 entries and compute the maximum brute force, just like you always do. Just do a loop from 25 to 28, compute the maximum. Okay. Okay, so what's the magic? Why do I do any of this pre-computation? What if I want to compute the maximum of A dot dot from 5 to 45? Okay, now this is where things get more interesting. I realize that A dot 5 dot dot 45 can be split into 5 dot dot 9, 10 dot dot 19, 29, 30 dot dot 39, and then 40 dot dot 45. These 3 numbers, I already have the maximum of. I already have the maximum. I don't have to compute them again because these are the whole blocks. I already have them. The leftover parts on the left side and right side, I do not have, so I have no choice but to do them brute force. So in general, whatever range I have will have some leftover and left and, some right and in the middle, there'll be chunks that are complete chunks, and these complete chunks have been computed. So the 2 ands, each of them can be done by brute force, which is again, at most big O of B time, because the 2 ands can be no bigger than the size of a block. And then you have to also look at the maximum of the blocks. How many blocks can you have? Was at most n divided by b. Because if you have, for example, n is 50 and the block size is 10, there are at most 5 blocks. So there are at most 5 of these chunks that you have to add. You have to take the maximum of. So this way, so this is kind of like the segment tree approach, but except that we don't recursively subdivide. We just divide it in one level, but each level, in the first level, the only level, we divide it into more than 2 blocks, a bunch of blocks all of the same size. And then if you are trying to figure out what a range is, the range will always cover a certain number of, possibly 0, but a certain number of complete blocks in between. And then there's some leftover things on the left, some leftover things on the right. To get the maximum of the leftover things on the left and right is at most big O of B, big O of 2B if you want. And then to get the stuff in the middle that are complete blocks, it's limited by the number of blocks, which is n over b. Does that make sense?
Yeah.
Okay. So then the question then is, what should B be? Right? So what is the size of B? How big should B be to make it good? Okay, so in the very worst case, right, you might say, well, let's make B to be exactly n. So only 1 block. And then in that case, you basically have the original naive representation. So when you make B is equal to n, then you have this part reduces to n, and this becomes n over n, which is nothing. So then all your work is on dealing with the leftover parts, which of course is what you expect because you basically have no blocks. What if you do binary, right? You say the segment tree approach, you split it into two parts. So size is n over 2. Well, in that case, updating takes n over 2 time, which is not good. Also, query takes n over 2 plus n divided by n over 2, and that cancels the 2. So the 2 doesn't really matter. N over 2 is the part that matters. Well, what if you make it to, I don't know, a third? Well, then this becomes n over 3, and this becomes n over 3, and this becomes bigger. The point is that when you make the block smaller, then these numbers get smaller, but this numbers gets bigger. So what we want to do, one of the things that you might remember is that when you have big O of two functions, then that's the same thing as big O of the maximum of the two. So for example, if you have n squared and then n, you only keep the one that's bigger. So by making b smaller, you're going to make n over b bigger. And the best thing to do to make the overall maximum of these two things as small as possible is to actually try to make b to be about the same as n over b. If you can make the two roughly the same, then you kind of achieve a good balance. So how do you, if you want to make them both the same, then you can kind of cross multiply and get this much, and then you'll see that b should be about square root of n. And so the answer, what b should be, is that b should be square root of n, or you round it up or round it down because that's usually not an integer. But let's just say approximately square root of n. And in that case, updating takes square root of n time, and querying also takes square root of n time. So we go back to the previous, this one. If I use this, it's sometimes called square root decomposition of the problem. You break it into square root number of blocks, each block has size square root of the original. Then both of these, it's square root of n time, which is of course not as good as log n for most n big enough, but it's potentially better than the standard representation, at least in the worst case. And some people will argue that if they're not used to writing this segment tree or recursive way of doing things, some people may say that doing the square root decomposition is easier to code. But anyway, now I want to show you, actually there are these problems, but maybe I want to show you my repository because, where is, no, it's not here. Code library. This repository is available to anybody. And I do have range minimum and range maximum query. But if you go to source, this is the code library that you might be familiar with. You look everywhere and you will not find anything. You can scroll down and up and down, but you won't see anything because this is considered a little bit more advanced. So it's in this special folder called ICPC. The ICPC folder is actually a folder, a code library that we take to the world finals and higher sort of level of competitions beyond the regional, because they have special requirements. For the regional, you can bring whatever you want, but in the higher level of competition, you can only bring maybe 25 pages, depending on which level it is, 25 pages of stuff. And so we won't bother taking things that's we think are not that, at least for the top team, maybe they think that there's no point taking Bicep because they can code it by hand. Anyway, so it's usually in, I think the latest version, well, okay, the latest version is the algorithm book, but let's just go to book. And then there's a bunch of stuff, and one of them is RMQ. Where's RMQ? Here it is. So there's RMQ, call construct RMQ to get some data structure M. M is basically the thing that the segment tree that I told you about, the ST that I talked about. The array A is what you're trying to build it from. Now, you might say, well, this doesn't look the same because it's not recursive, but it's really the same thing, but it's kind of flattened out to not use recursion. But you'll see something like, for example, this code here. This is kind of what I wrote, right? MI, and then this is a 2i plus 1 and 2i plus 2, which is the left and right half. But anyway, this is written in a way that you don't do recursion, I guess. And then here, get max, it's very similar to what I told you. You do a mid, and then you do recursively do left and right. The update is also very similar, but this time it's not recursion. Anyway, there's RMQ here. And then there's no segment tree here, but in the other, so this book was the one that we used for 2013 and 2014 World Finals. And then Joseph added some more things for the North American Championship in 2020, just before the pandemic. That was our last trip. And then he added a bunch of stuff, and segment tree is in here. He has two versions, but the way that he wrote his segment tree, probably only he knows what to do with it, because he tried to generalize it by writing a function so you can specify what it is that you want to compute, whether it's adding something in a range, so you have a function that add things, or you can have a function that pick the maximum of two things, or whatever. So he gives some example. For example, a segment tree that has add, this is how you do it. A segment tree that picks the minimum, that's how you use it, and so on. So there's a query function, there's an update function, and then there's a constructor. And then segment 2 is something that's a little bit more tricky, so maybe I'm not even going to talk about that. Yeah, I'm not going to talk about it. But anyway, we have code for that. That's what I want to say. So now I'm not going to show you solutions to these problems. I kind of want to show you some of these problems where these type of data structures can solve. Okay, so this problem is called supercomputer. There's a big story that has nothing to do with the problem, but anyway, this is where the meat of the problem starts. You have an n-bit memory. Okay, so you have n-bit memory from 0 to n-1 indices. What can you do? So you can decide to flip the kth bit of the memory from 0 to 1 or 1 to 0. And given L to R, you want to know how many bits in this range are set to 1. Okay. And then the problem basically gives you up to 1 million bits, up to 100,000 queries, and the queries are either change a bit, flip a bit, or ask for a range, right? So basically, in this case, you can use the sum, right? So your underlying array would be binary 0, 1. When you update it, you just update it, either change it to 0 to 1 or 1 to 0, and then to get number ones in a range, you just basically add them up. This problem can also be solved by Fenwick tree, because it's basically, when you have sum, you can just use partial sums to arrange. So either way it would work. But the main thing is, you have some kind of a range. You have a bunch of queries, and in these queries, you interleave between changing stuff and also asking for querying the range. When you see that, you should think about segment tree in some way. Okay, so this is a fairly straightforward application of segment tree, especially if you already have the segment tree code. All right, again, the worst weather ever. There's a bunch of story, but anyway, so let's skip the problem. Your task: given information about the amount of rain during different years in the history of the universe, and a series of statements, year X had the most rain since year Y. Determine whether these are true, might be true, or false. So what a statement is true if the amount of rain during these 2 years and all years between is known. It rained as much during year X as it did in Y. And for every year Z between Y and X, the amount of rain during year Z is less than the amount of rain during year X. Okay, so you have basically you're given a Y, a year Y, and a year X. You want to know if year X had the most rain since year Y, so you have some numbers. Okay, so I'll just put a star to mean you have some numbers. So first of all, if X really has the most rain since year Y, what are the things that you must know? The amount of rain during these years and all the years between are known. So every one of these years in between, as well as Y and X, you have data for it so that you can check relatively easily. It rained as much during year X as it did during year Y. So if this, I don't know, this is let's say you have an array A indexed by the year, then A bracket X has to be at least as much as A bracket Y. Again, that's relatively easy to check because you just look them up. But now this is the harder part. For every year in between X and Y, the amount of rain during year Z was less than the amount of rain during year X. So A bracket Z has to be less than A bracket X for all Z that are between Y, between Y and X. That's what it's saying. So what do you do? Well, if you ask for what is the range maximum, what is the max of A from Y plus 1 dot X minus 1, if you ask for the range maximum of this range, that would be the biggest number in this range. And this biggest number in this range better be less than A bracket X. That's what you need. You need to check that everything in this range, even the biggest one, is less than A bracket X. And of course, you can answer this question by range maximum query. And this is where the range maximum query comes from. What else do you say? Now there's also the maybe. So instead of checking that something is true, it's also possible it may be. So what is maybe? Maybe means that we say that such a statement might be true if there's an assignment of amount of range to years for which there's no information such that the statement becomes true. So any of these could be a question mark. Maybe you don't know this one. Maybe you don't know this one. Maybe you don't even know this one. Okay, maybe you don't even know this one. Who knows? So if you don't know this one, then it's easy. The answer is always maybe, because you can make this as big as you want, and then everything is okay. If you don't know this one, then it may or may not be true, because you still have to know what is the range maximum of this range, at least among the ones that you know. So it turns out that these numbers, the question marks, doesn't matter at all because you can make them as small as you want. So again, basically, you still want to know what is the range maximum, of the known ones. Okay. And then if this is the one that's unknown, well, then you can make this small, but then you don't know if this range, it's the maximum is bigger than a bracket x, then it doesn't work. So basically, these are the possible situations that you have to check. There's one extra problem that you have to worry about. The problem is that the year that they give you can be up to a billion, actually plus or minus a billion. So your underlying array, at least conceptually, it's like this, which is really big. It's 2 billion entries. And if you build the segment tree the way that I tell you, you're going to run out of memory. There's no way you can actually do it. So what do you do? Now, this is a little trick here. Even though this range is large, you will notice that they tell you that the amount of information they give you, it's at most 50,000. So even though the range itself can be really large, they're really at most 50,000 different numbers. So maybe there's 0, maybe there's 30, and then maybe there's 72, and so on. There might be a bunch. Okay, but they're at most 50,000 of these numbers, even though the largest one may be 10 billion, 1 billion. Okay. So what you do instead is you can build a segment tree on 50,000, but then in your node you wouldn't be storing the range. You wouldn't be storing the range, just the range, the index from 0 to 50,000. You would also probably store the range of the year. Okay. Then you know both the array index, which is 0 to 50,000, or 0 to 49,999, and also the range in a year. And then you have to be careful how you interpret the results. Right? But as long as you keep that little information available, you should be able to figure out how to handle all of this stuff. But again, the idea is segment tree. Okay, maybe I'm not going to talk about the. Okay, maybe I'll just quickly show you this other one. Maybe I don't want to say too much because again, there's. So for some reason they like to have these big description. But anyway, basically they're N people, they're N pirates. They all have unique ID from 0 to N-1, and they all stand one next to the other. Okay, so 0 to N-1, N is at most basically 1 million and a little bit more. Then each of these people is described by basically a single bit. It's either 1 or 0. Okay, so they say, okay, let me try to figure out how to show this. Each pirate is either assigned a buccaneer or Barbary pirates. Buccaneer is described by a 1. Barbary is described by 0. So basically you have a binary array, 0 and 1. You have to build a string of the pirate description. Each case starts with M up to 100. And then M pairs follow. Each pair first has the T, and then a string of 0 and 1 of maximum length 50. Then you concatenate a string T times. Okay, this description is kind of very long and convoluted, but let's just go straight to the sample input. Sample input says that there are two entries. First entry is the binary string is 10, and it's repeated 5 times. So repeat it 5 times like this. That's what this 510 means. Take it at 10, repeat 5 times. Then the 1000, it's repeated 2 times. So that's what this thing says, and results in this string. Okay, then what can you do? You can try to flip. Okay, what are the indices? Okay, so 0 to 17 is the entire array. F means flip all of it. So if it's, wait, hang on. Is F flip? No, sorry. F means change it all to 1. Okay. Okay, where is my, scroll back kind of. So my, hang on, let me just erase this because this is getting confusing here. Okay, so F just means change everything to 1. E means change to 0, change the whole range to 0. I means invert, so flip the range from 0 to 1 and 1 to 0. And then finally, S, it's basically counting. So S, I believe, is query. S is query. Query what? Number of ones or number of zeros? I don't remember. How many Buccaneers? What? 1. Okay, so query number of ones. So in this case, yeah, you basically do the same idea of segment tree. So you take this range and you divide into different parts. In this case, I guess you can be even more how do I say, tricky if you want. So your node could actually instead of storing this string, if you want, you can actually so which string? Yeah, 5 times 1 0. If you want, you can actually store just 1 0 once and say there are 5 copies, but then you have to realize that this node covers the range from 0 to 9. And then you can basically implement all of these operations by following the segment tree. It's not completely trivial, but it's turns out to be not so bad. Anyway, it might actually be easier to not do that, because it might actually be easier to not do the tricky thing, because when you have with your one node that goes from 0 to 9, but then sometimes somebody say, I want to flip, or I want to fill the range, I don't know, 4.6, then this one node that used to talk about 0 to 9, repeat it with 1 0, repeat it 5 times, and then have to split because this pattern no longer holds. And then you have to introduce some mess to deal with that. So it might be actually easier just to have a standard segment tree and then just deal with that way. Okay, so I don't want to show code about these problems too much, but I think what I said here, this code that I show here, it's good enough. Plus the fact that you have the code library to refer to for segment tree. So this is definitely something that I would say it's towards the top end of what is expected at a regional contest. So by that I mean teams that are expected to be top 5 in the region should have absolutely no problem if they see a standard segment tree problem. They should just go to the library, do it, and then hopefully done in, I don't know, 10-15 minutes. But it's a big gap between the top ones and so the people in the middle, because the people that are in the middle may not even have any idea of what a segment tree is, right? So this is definitely at the sort of a higher end content, but at the same time, it's not that hard to understand conceptually, I think, especially if you're used to binary trees, but it might be a little bit hard to, of course, to apply it. So if you have time, try these problems. I guess that's it. That's it for what I want to say for this week. Okay, now